Hello all, I welcome you all to the 19th lecture in this course E614. The last time we met, we spoke about BJT, we introduced BJT and spoke about the common base output characteristics and common emitter output characteristics. While we discussed many aspects of this, I wish to emphasize a bit more on certain aspects of the output characteristics before we go on to today's topic, which will be the non-ideal behavior in BJT. The first and foremost is the stark difference in the output characteristics of common emitter and common base. So let's say I'm going to draw the common base characteristics again. So we saw that if in the common base, if the emitter is open, then if I vary the base collector potential, I have a very small increase in the current, which is the normal reverse bias current, but we'll actually, this is not VCB, this is actually VCB. And then if you increase it further, then you have a breakdown, which we saw previously can come from many means, right? And we saw that the collector current follows mostly the emitter current, because under most situations the base transport factor is almost equal to 1, right? And this is increasing emitter current characteristics. The very moment that you change the base potential higher than the collector potential, in the sense that you have a VCB which is negative, we saw that immediately the current starts dropping, right? And the question is, why does all of them drop to the same? So this is the zero current condition, IC equal to 0 is here, right? Did you think about why all of them drop to the same VCB, some negative value? The reason why IC naught becomes 0 is, let us take this is the base collector, right? And let's say at any IE, right, you have the NP naught value proportional to IE, proportional to the VBE, right? And every time IE increases, it obviously means that I have higher and higher minority charge injection from the emitter side, right? And the condition for IC to be 0 under this situation is you are now forward biasing the base collector junction as well. So you have electron injection on this side also, right? So you start increasing the injection from the collector side. What this condition saying, that irrespective of what is my electron injection from the base, the total current becomes 0, or the electron gradient in the base becomes 0 at the same collector base potential, in the sense that my actual injection from the collector side is the same value, but still the gradient drops to 0 irrespective of my injection from the emitter, right? One has to wonder why that is so. The actual reason is you have electron injection or hole injection from the base side, right? So because when you are forward biasing the collector base junction, you are injecting holes from this side, and the holes do not contribute to recombination here, but are just swept across this junction. So whatever holes that we are doing, you have no recombination in the base, you have no recombination, you don't have any, you have much less holes moving in this side. So the electron, irrespective of what is the injected density here, a very few of them get recombined because all the holes which are injected to the base are either swept to the emitter side or swept to the collector side, giving you very low hole density in the base, giving you a very low recombination efficiency in the base. And hence what happens is you have a very small gradient in the base leading to zero current irrespective of the emitter injection density or emitter current, right? So all of them fall down to the same value. And it can also be seen that the very moment you change the potential, which can be contrasted in the common emitter case. So let us plot the common emitter case. This is common emitter, right? And you know that the saturation does not happen at one single point, and then you have a saturation parabola, right? So you have something like this. And we also saw that the gradient is almost the same, but then you always have a gradient in the sense that you have an IC which is proportional to VCE at all IBs. IBs are increasing. Another point that should have been mentioned, probably I did not mention it well enough, is the actual ICE naught, that is the IB, open IB in the common emitter case, and ICB naught, that is the open collector base in the common base situation, the open emitter configuration, right? So it's always that ICE naught is much larger than ICB naught. We will see very soon why this is the situation. We have to know this because it is crucial. It depends upon, this determines which is your choice of configuration to use, right? And the reason why you have this parabolic change in the saturation, so this is your saturation region. Why is this true? If I increase the base current, I need to have a larger and larger collector potential to actually put it in saturation. Why? This comes from the fact of the way these are connected. So let us once again compare these two, base, collector, emitter, base, collector, right? In the common emitter case, you have something like this. And in the common collector, in the common base scenario, you have something like this. Right? So you can see that in the situation where you have the common emitter, the actual common emitter potential is a summation of CB plus VBE, right? So any increase in the collector potential also increases the base emitter potential, which will reduce the collector base potential, right? And hence you need to provide more and more common emitter potential for an increasing in the current. If I have to increase IB, I have to increase the base emitter current, right? So if I increase the base emitter, if I increase this one, I have to increase VCE to actually have VCB in the positive side, right? To have it in the reverse bias situation. So with that being given, now let us consider the situation of why in the common emitter case, the collector emitter current is much larger than the common base scenario. So this is the common base scenario, right? In the common base scenario, if my emitter is open, so that means that there are no currents here, right? If there are no currents here, there is no electron gradient here. So the electron concentration remains flat. So because we are talking in the ideal situation where the current is mostly carried by diffusion, the loss of electron gradient in this particular part of the BJT actually significantly reduces the base emitter reverse bias current even lesser than the normal reverse bias current. So in the sense that ICBO is even lesser than just the reverse bias current. I mean collector base reverse bias. This is an important statement in the sense that if emitter does not exist, right, that's the normal reverse bias collector base junction. So this BJT with the emitter open has a current which is even lower than what is the reverse bias current that you will achieve when you have simple collector base junction reverse bias. The reason behind this is that you have significantly reduced the region of having diffusion, where because you have put because you have a PN junction with which is junction which is open, so you have ensured that you do not have electron gradient in the emitter side, and you will have some electron gradient in the collector base side which is much smaller than what it was before, right? So basically you have a much smaller reverse bias current, whereas the situation where you have the common emitter open situation, so this is in this case you can see that when the base is open you still have current through this, right, and then you still have a gradient in the base emitter junction. So you kind of have the base at a potential which is always higher than the situation in the common base scenario. So you have a ICEO which is always higher than ICB naught, and we can always compare this with the previous relationship that we derived. So we saw that ICE naught is basically ICB naught by 1 minus alpha. So alpha t being the base transport factor. So if this value is almost close to 1, so you can see that ICE naught is always much larger than ICB naught, right? Alright. So in addition to this, just because of the fact that you have a much smaller ICB naught, you can also understand why the avalanche breakdown in the common base region, in the common base configuration, is much larger, right? So the third point that I want to emphasize here is the avalanche breakdown in the common base scenario is much larger. Breakdown voltage is much larger than in common emitter case. All these things stem from the fact that the common emitter has much larger currents than in the common base scenario, which can also be taken from the gain that you will have, right? So your common base gain is almost equal to 1, but whereas your common emitter gains are much larger, right? So the typical relationship between VBCEO, so VBCEO is the common emitter scenario breakdown potential is VBCBO into beta power 1 by n minus 1 by. So beta is the gain, and VBCBO is the avalanche breakdown point in the common base situation. So this value is always much larger than the breakdown potential at the common emitter scenario. All right. So with this, we will continue on the non-ideal scenarios. So that is the actual topic of discussion today, which is non-idealities in BJT. Right. So let us start with the first non-ideality, which has to do with emitter band gap narrowing. The reason why this happens is our greed to have a higher emitter injection efficiency. So we need a higher emitter injection efficiency always. So which is defined by gamma, which is INE by IE, right? So this from our previous relationships can be written as NP naught. N is the minority carriers in P, dn diffusion current, diffusivity of electrons, and width of the emitter. If we look back at the INE, you will know what I'm talking about, and IE will turn out to be Pn naught dP ln tan h W by ln. I want you guys to go back to the previous derivations that we had, and you can see that this relation falls down pretty easily from there. So this is the emitter injection efficiency. Now for us to increase this particular value, you have to increase NP naught and you have to decrease Pn naught. So how do we increase NP naught? So NP naught is the minority carrier density in the base. So the way to increase NP naught can be increased by reducing the base doping, right? Because of law of mass action, you know that if you reduce base doping, you can increase NP naught. And base doping is given by the Gummel factor, Gummel number, right? Integrated doping density in the base. Another way to increase injection is reducing Pn naught. How do you reduce Pn naught? By increasing the emitter doping density, right? We can reduce Pn naught, that is the hole density in the emitter, n-type emitter. So we can reduce Pn by increasing emitter doping. But increasing emitter doping, which is what typically done in many cases, you have a very narrow emitter with heavy doping density always, right? But then increasing the doping density much further has other issues. The first issue is you increase Auger recombination rate. Why? Because this goes linearly or proportional to the emitter number of electrons in the junction. It is typically n square, right? It goes as n square. So higher the number of electrons that you have, higher is the Auger recombination efficiency. So typically you have an emitter recombination rate much higher when you have very high emitter doping density. The second point, which is typically considered when you have higher emitter doping, is what is called as band gap renormalization. So band gap renormalization happens when you increase the doping density. Why? So let's say I have a semiconductor like this, and I increase the donor doping density. I increase this mid-gap state so much that actually I never have any excitation events from the bottom of the valence band to the bottom of the conduction band. So what happens is, because these states have lost an electron to the conduction band and almost are empty, and this state density is almost close to the conduction band density, because that's what happens when you have very high doping density. So you have most of the excitation happening from top of the valence band to the defect states. So this is one such reason why you have a band gap starting to renormalize. This is a hand waving argument, but the actual renormalization value should have to be calculated from first principles. So typical change in the band gap for increasing doping density follows this particular relationship, about 18.7 ln of n by 7 into 10 to the power 17 milli electron volts for n larger than 7 into 10 to the power 17. This is some empirical equation, so which says that as I increase the doping density more and more, higher than 10 power 17 per centimeter cube, I'll start having band gap which will start to reduce, right? So when I have del G which is reducing, so you can clearly see that the Ni square is Nc Nv e power minus Eg now effective, right? Because I have reduced by Kt, which can be written as Ni naught. That is the situation where I have not included the effect of band gap narrowing into e power del Eg that I have previously calculated by Kt. And under these situations, my Pn will turn out to be Ni emitter square by doping density in the emitter, which will turn out to be Ni naught square by Ne e power del Eg by Kt. So the actual emitter injection efficiency, which is proportional to 1 by Pn naught, as we saw, now goes to be proportional to e power minus del Eg by Kt. So the high doping density which we actually introduced to reduce Pn naught also started to increase the minority concentration in the emitter side because of the band gap narrowing situation, right? So this is the non-linearity or non-ideality leading to from the caused due to band gap renormalization because of very high emitter doping density. The second non-ideality we will deal with is what is called as the Kirk effect. So what happens is, if I have a very high injection from emitter, the base collector junction depletion becomes sort of undepleted, because now I have injected densities as large as the actual doping density in these materials. So what happens is, so much of free flowing charge in the base collector junction. So let us take, I have something like this. I have emitter in base collector which has to be depleted, right? So yeah, my actual carrier density should be like this. This is Np naught, right? But then that's not what exactly happens. So what happens is, because I have such huge density that is being injected, the depletion width in the base emitter junction kind of moves to the collector side. So if I draw the band diagram at very high injection, I will have the so because I have very high injection, I do not have the small barrier in the emitter base junction, because the emitter side is so forward biased that you do not have any barrier there. And the collector side, what happens is, I have a collector contact. So basically at this point I have a collector contact which is N++. So this is the N-type collector, this is the P-type base, and this is the N-type emitter, right? And I have a N++ kind of a collector. So I have an N++ junction which will also be which will also have some sort of a band bending, right? Because caused due to just N++ kind of a junction. So I will have some kind of a band bending here. So this is, so I have a emitter base collector, and this is N++ contact to the collector. So what happens is, my actual if I draw the charges, this is base charge. In the emitter side, I have a positive charge, right? This is P, will start to have negative charge. And instead of actually having the depletion width here, This is the ideal situation when you have very low injection. But instead of there, because you have so much of charge injection here, the depletion width moves away from the base collector junction, and you form the actual depletion width here in the n plus plus junction. So you have a very high, because n plus plus is a super heavily doped collector contact, so you have a very high charge density here, and the n collector, mildly doped n collector, acts almost like a p-type junction in front of the n plus plus collector contact, and then you have a very small and you have a depletion width in the n site region, which will have this kind of a thing, right? So when you have the charge density like this in comparison to the actual charge density, which would appear like this, you can draw the electric field similarly from the Poisson's equation that we previously saw, right? And in the ideal case, you should have an electric field like this, right? You have a dip in the field, much smaller dip in the emitter side, a reasonably larger dip in the base side, and you have PN junction, reverse bias, so you will have positive charges here and then a much slower decay, right? And because you have a n plus n junction, the electric field will look something like this. This is the ideal case, ideal low injection. Now if I have a very high injection and I have a very large amount of charge density in the base collector junction such that none of the charges, so basically see, how did we get these charges here? The reason we got these charges is we wrote the charge neutrality situation, that is n plus Na plus equal to P plus Nd minus Nd plus, sorry, right? So this is the actual charge neutrality situation, right? And we always took the ionized dopant charges to contribute more than the free flowing charges, because we always talked about low injection in the PN junction we spoke before. But in this very high injection situation, we will see that your N is almost equivalent to Na plus and P is almost equal to Nd plus, and hence under these situations you can always have a situation where you have zero excess charges in the base collector junction, and hence when the Kirk effect dominates, your actual field will look like this. It will remain flat, and you will start to have a depletion with much larger in the N plus P junction. And if I have a very high current density, I will have something like this. Very high injection. So I will not have any depletion in the base collector junction, but then I'll start having depletion in the collector contact junction, and hence the actual width of the base, now instead of the width of the base being here, so this was the original base width, right? Now because of the fact that I have the actual depletion width moved to the other end of the collector, the actual width of the base will be this. So this will be WB plus WC. So your actual base width now become multiplied, right? Now it became multiple fold of its original situation. Hence you have a very large base width, and you know what typically happens when you have large base width, right? So this is what is called as the Kirk effect, where you have moved the depletion width from the base collector junction to the collector contact junction. So this is the second non-ideality that we saw. Now let us go to the third non-ideality, which is current crowding or base spreading. this is coming from a practical device application perspective. So let us take a, a normal BJT, how it is formed. So you have an emitter, you have an emitter contact, and you have a base beneath it. So this is base, and then you have a collector, and then you have a collector contact. The actual dimensions are not are not drawn to scale, right? So basically your base is typically much smaller than the collector size. So this is my mistake. I have just drawn this like this to show the the property that we want to discuss today, which is called as base spreading. So what happens is, if you want to inject electrons to the base or inject holes to the base, you can see that any injection, the current will start to crowd in these regions because this is the shortest, the least resistive path, and very few will actually go here, right? So the actual emitter base area got reduced. So this is the actual emitter base cross section, right? It has to be here, but instead of using this entire region, the actual injection from base to the emitter happens only in this area. So the actual injection cross section or emitter base junction area gets reduced because of the contact architecture. So what happens is, your actual base resistance becomes much larger. Right? Because if the cross section area drops, of course, given the same resistivity of the base, you have a much larger resistance. So what happens is, your actual potential which falls, so your V forward bias or VBE is much smaller than VBE at the terminal. Why? Because VBE at the junction, this is at the junction, so VBE junction plus V base resistance will give you the actual VBE at the terminal, right? So if the base resistance potential is larger, so you will have an actual lower base emitter junction potential, and hence lower current, and hence as you start increasing the current density, let's say this is VB at the terminal, instead of having a linear relationship, you will start having a reduction in the current for the, so this is the current loss due to base spreading resistance. And why does it dominate at higher currents? Because at smaller currents you can see that your current will start, so your current, so basically your current will start to be injected in these areas, will be having the electron density will have enough space in the emitter base junction to be injected, and hence you really do not have a problem. But once you start increase the current, your actual injection cross section needs to be larger for the increased current density, right? So it is often observed at very high injection currents or very high collector currents, where you start to see the effect of base emitter junction reduction area because of current crowding, right? So these are the three non-idealities which is most often discussed. So we will stop now. In the next lecture we will deal with the dynamics of charges, like we saw about charge storage in the PN junction. We'll talk about some dynamics in the BJT which limits its cutoff frequency and basically the maximum frequency of operation. Thank you.